This is hurdy-gurdy, a platform for deterministic, fidelity-graded translations between formal languages. It implements the calculus from the paper, Untrusted Authors, Trusted Answers, available as an archive preprint from the repository. The idea, in one sentence, to answer a question about a program, move the program to where the question is decidable without ever trusting an unaudited step. Before anything else, an example. This tiny C program reads a byte, doubles it, adds one, and asserts the result is never 128. Can the assertion ever fail? Hurdy-gurdy answers by moving the question. A pinned C compiler translates the program to RISC-V machine code. Then a translator written from the instruction set manual turns that code into beta 2, a bit-level transition system where a model checker decides the question outright unreachable on every input. The answer is carried back to the C source line where the certificate and independent checker revalidates. But there is a second way down. The same RISC-V code also reaches beta 2 through SAIL, the architecture's formal model, and the two roots must agree. One question, two independently built roots, one checked answer. Keep this picture in mind. The rest of the video explains why each step deserves trust. Before the mechanics, the vision. Hurdy-gurdy is built as a two-directional experiment in LLM-generated correctness. It bootstraps LLMs toward correctness. In one direction, LLMs develop hurdy-gurdy itself, independent agents write every pair, and the architecture's cross-checks are the only semantic gate. In the other direction, LLMs use hurdy-gurdy to generate correct code, answering questions about programs through deterministic graded checked moves. Nearly all code is LLM-generated, the human contribution is the architecture. And the same gate is the growth model. Anyone, an LLM, an agent, or a human, can add a new language pair through an ordinary pull request, admitted by the architecture, not the author. The paper calls the two sides two planes meeting in one registry and keeps them apart by design. Answers never write, growth never answers. You have just seen a C program's reachability question become a model checking problem. Elsewhere, a Python assertion becomes an arithmetic query. Every such move is a translation, and every translation is a place to be wrong. Classical responses, certified compilation, and translation validation are statements about a single edge. But in practice, representations form a graph, many source languages, several solver-facing targets, and, as the example already showed, more than one way to get from here to there with honestly different trustworthiness. The unit of the platform is the pair, two formally defined languages and four pure functions. Take the example's first hop from C to RISC-V. A translator, here the pinned compiler, an interpreter for each of the two languages, and a target to source interpreter that carries a solver's answer back to the source, the way unreachable came back to the assert line. Together they close a commuting square. Interpreting the source directly must match translating, interpreting the target, and carrying the result back. The square commuting is the pair's correctness statement, and a point where it fails to commute localizes a translator bug. And exactness is not the only honest claim. Squares are directional. A translation may over-approximate its square commuting up to a declared direction, with exactness as the special case. The direction is part of the pair's contract, checked per program. Everything is deterministic. The same input produces byte-identical output always. And pairs do not pretend to be equally trustworthy. Each declares a fidelity grade, predicted when the output is foreseeable from a written specification, reproducible when it is only pinned, checked when it is validated against the source on every run, proved when a machine check proof accompanies it, and trusted, which assures nothing and never ships uncovered. The example already used 3 of the 5, a reproducible compiler, checked translators, and a proved answer. Its unreachability certificate revalidated by an independent checker. Pairs compose into roots, which inherit determinism, and a root's contract is the meat of its hops, assurance, direction, kept observables, and cost. A root is only as faithful as its weakest pair. But roots can branch, and the example's fork is the canonical one. RISC-V reaches beta 2 along two roots directly, with a translator written from the instruction set manual and through SAIL, the architecture's formal model. The two translators were built independently, and that independence is a resource. Agreement corroborates both routes, while disagreement localizes the bug to one pair. Branching turns several merely checked pairs into a jointly stronger guarantee. The example spine sits inside the registry, 13 languages and 15 pairs, organised around two reasoning hubs. Two of the pairs are abstractions that loop on the beta 2 hub itself. Beta 2 for bit-level model checking is reached by C through RISC-V and by front ends for the 64-bit ARM architecture, WebAssembly, eBPF and the Ethereum virtual machine. SMTlib, the theory-rich hub, is reached by chemical reaction networks and by a Python fragment, and a bridge connects the two hubs. And here is the experiment. Every pair, translator, carryback and tests was implemented by an independent LLM agent from a one-page brief, largely unsupervised, with the architecture's cross-checks as the only semantic gate. The platform's intended player is also an LLM. It chooses questions and routes, but can take no unchecked step. The compositional core of the calculus is mechanized in Lean 4. Trust comes from the architecture, not from the author. The paper reports measurements, not aspirations, per construct coverage, counted only where a construct is both covered and faithful. Branch agreement along the example's dual risk, 5 routes, and the same branch on ARM, with machine-derived ground truth. Certified unreachability, revalidated by a formally verified checker, and the defects the architecture caught, including 1 in the certificate pipeline's own checker adapter and 3 in its own measuring instruments. 2 more measurements close the loop. A seeded mutation experiment puts a number on the gate's own escape rate, and its first round exposed a blind spot in the gate's probes. In the player experiment, an unaided model answered 7 of 8 hard reachability questions. The same model, playing the platform cold over its machine interface, answered 8 of 8, each with a machine-checked evidence artifact. Why the name? A hurdy-gurdy is an instrument whose player cranks a wheel and the mechanism turns each choice into sound the same way every time. The translator is the keyboard, same key, same pitch. The interpreters are the wheel, and the player, an LLM or a human, decides what to ask. Read the paper, Untrusted Authors, Trusted Answers, a calculus of fidelity-graded translations, and explore the code, the evidence, and the lean mechanization on GitHub.